Okay, we have a few diagrams here we can use to create free body diagrams. So free body diagrams are diagrams with forces, so they're sometimes also called force diagrams. These diagrams don't have to be detailed with any shape or exact situations of the object in question. They just need to have all the forces in the diagram and the relevant angles in the diagram and also axis, x and y axis in the diagram. So let's start from the top left. This one is a static equilibrium. So we have this sphere hanging below the string here, and we can analyze by analyzing this location right here. So this is basically a massless junction, but it's okay. So we'll analyze first. It gets pulled here this way to the left, right? So we can let's use a different color. So we can add a tension toward the left, and we can call it T left. Another tension toward the right. Just remember that these are forces, right? The forces are different from these actual strings, so we don't want to draw the forces as long as the strings, and somehow have the wrong impression that the right side has a longer string, so it has to have a longer force to go with it. And it turns out it's not necessary. So we don't need to be bound by the physical object, the strings. We just need to be bound by the direction they give us. And there's also this downward tension, and the downward tension is equal to the gravity of the ball in magnitude, right? So this is a complete free body diagram. We'll just need to add axes. So this is not exactly vertical. Okay, so we'll have a y-axis. We'll also make this into a solid x-axis. So that's an x-axis. So to complete this diagram, we want to decompose this tension into its horizontal. So this is TRX, and also vertical. This is TRY. And we'll do the same thing for the TL, the left tension. TLX. And this has TLY. So now we have a complete free body diagram. It has axes, it has this object in the middle, it has all the forces are originating from the center. These are all the features of the free body diagram. It also has the angles already. So the next step, if you have some details of the tension, you can start decomposing this tension into its components, decomposing this into its component, and do some balancing. So our focus here is just to draw the diagram. We don't actually solve problems. Once we have the diagram, we should be able to solve problems if we were given enough unknown quantities. So let's move on to the next one. This one is accelerating to the right because there's a force pulling and there's no friction. So we start again. Now we can focus on this physical object, the center here, and we draw gravity from the center, Fg or W, whichever you prefer. And we also have normal force from the surface. So if you want to draw where the force is applied, you probably want to start from here, right? But this is difficult because if you put all the forces to originate from this point here, it's easy to decompose them into components. It's also easy to get them to combine along an axis, easier to see, right? So we remove that. We start from the center again, and we draw a normal force, F normal or just normal. And then we also have this applied force here, which is just trace it. Okay, it's F1. So since there's no friction, there's no more force, and I want to complete my diagram, I want an axis. Let me get something to draw with. So this is my x-axis. Should have used this. Nope. The y-axis. Okay. So again, there's one force that's not along the axis, so we decompose it into F1x and F1y. And here's the angle. So in case you need one, F1x is this adjacent in this right angle triangle. So it's F1 cosine 35 degrees. And F1y magnitude is F1 sine 35 degrees. This side I didn't do it. I should probably go back and do it. So TRX is TR cosine 30 degrees. TRY is TR sine 30 degrees. And TLX is TL cosine 50 degrees. We need to be careful. This is just magnitude. So when you're adding the forces together, this is a TLX. It points toward the left. So when you're adding, which is next step after the diagram, you want to consider the sign. And TLY is TL sine 50 degrees. All right. So now we're done with these, and we also have this one here, a box on an inclined plane. So let's first draw gravity. Gravity is straight down. Okay. Fg or W. And normal force, as I discussed in the previous video, it needs to be away from the surface is perpendicular. So I'm drawing perpendicular from the surface. Not vertical, but perpendicular from the surface. And I also have this applied force. Let's call this F1. So now with these forces, because I expect the acceleration to be along the inclined plane, either up or down, depending on how F1's upward component compares against gravity's downward component. But the motion is going to carry out along this axis, and perpendicular to it, there's no motion. So it is advantageous if you do an axis along the direction of motion, then the cross axis has no acceleration. So now I want to choose this to be my x-axis. So this is my x-axis, and then that means the y-axis needs to be perpendicular to the x, no longer vertical, just needs to be perpendicular to the x. This is my y-axis. So they're rotated. Exactly how much are they rotated? They're rotated the same way as the same amount as the inclined plane. So I can do dash line here. This is a horizontal line. This is the same as 28 degrees. Be careful, I have two separate angles here. So 28 degrees rotated. And we drew the forces out. We decided our axis. Now we should decompose the forces. So this F1 here needs to be decomposed along this new axis. So this is F1x, and F1x is F1 cosine 35 degrees. And across is F1y. Okay, got approximately correct. So this is F1y. And F1y is F1 sine, same angle, 35 degrees. And the normal force is along the y direction. And now we need to do the gravity. Gravity is no longer along the y-axis. Used to be typically along a vertical y-axis, but now y-axis is no longer vertical. So gravity needs to be decomposed. This magnitude, this component is FGY. So FGY is FG cosine, now it's the inclined plane's angle, 28 degrees. Alright, so 28 degrees, 28 degrees. If you ask me how I got this angle to be 28 degrees, well, the 28 is between the horizontal and the incline. And this angle is between the vertical and perpendicular to the inclined plane. So they should have the same exact angle there. So this FGY, also FGX, is FG sine 28 degrees. These are related to the inclined plane. And FGX is this direction. We have this FGX. Alright. And I need to point out the perpendicular. So here's a perpendicular. We're using this right angle triangle to decompose. So here's another perpendicular, right? Perpendicular is over here. We were using this right angle triangle to decompose that force, right? Perpendicular here. Okay. And let's just remember that each time you try to decompose a force, that force needs to be the hypotenuse of your right angle triangle. It cannot be any other side because it has to be the longest one to be decomposed into smaller components. I should probably also add a perpendicular here and here to indicate what the lines are doing, the dashed lines. Okay. And let's move on to the next object. And now we have a just focus on this this ball here. The other ones could just kind of a counterweight. So the ball is actually going in a horizontal surface. It's going on a uniform circular motion, a single object. So how do we do uniform circular motion for your body diagram? This is my trick. We want to do the x-axis. We want the x-axis to point toward the center of the rotation, which is here. This is the center of the rotation. Alright, so we want our x-axis to point in this direction. And it doesn't look very good. Okay, that's good enough. So this direction is x-axis, and we still want a vertical axis to be y. So here's our y-axis. Well, the reason of pointing the x-axis backward or toward the center is the acceleration in a uniform circular motion is toward the center. So by setting your x-axis toward the center, you'll have your acceleration pointing in this direction. So now we need to draw the forces out. So we have gravity down. And we also have tension pulling at an angle. So here's tension. Okay, tension is not along x or y, so we decompose tension. So this quantity is Tx, and this quantity here is Ty. Oops. Okay. So there's an angle here involved. This is the 35-degree angle. So that makes this 35 degrees. Also this angle 35 degrees. Right. So if we're looking at this right angle triangle, this one here, the 35 degrees is opposing the x, so x component should be sine 35, and y component adjacent, so it should be cosine 35. So here Tx is T sine 35 degrees, Ty is T cosine 35 degrees. And since we know the acceleration is due to forces along this direction, we can easily say that this force net is equal to this centripetal force. Centripetal force is not a force, it's just a net force. The same exact concept here. The net force that causes a centripetal motion, that would be called net centripetal force. So this now is equal to Tx, right? And if we knew more, we would say that okay, that's equal to what magnitude. Centripetal force has a certain given magnitude, right? So this is how you deal with centripetal or uniform circular motion, by pointing your x-axis toward the center of the rotation. So let's move on to the next one. This one here, see this is shaded, so this has friction against the box. Now we have a system of two boxes. We call this a connected system, a connected object system, because there are two objects. They're connected, they're moving at the same velocity and acceleration, assuming that the top box does not slide off. Since we have two boxes, we should have two free body diagrams. So let's see if we can pack the diagrams into the same exact this overall diagram. Otherwise, we'll just keep our separate diagrams. So usually for something like this with a stack of boxes, I'll start from the top one. The top one's easy. So I'll offset the dot, this is center, to the left, so I have enough space for the other diagram. So first one, I draw its gravity. So let's call the boxes 1 and 2. So it's a 1, here's a 2. So FG1. And it feels a normal force from the box below it. So normal force, let's call it 1, 2. So between the 1 and 2. And forgot to draw friction here. Let's just draw some shade here. So there's some friction going on between boxes 1 and 2. So if the entire system accelerates toward the right, then if there were no friction between the boxes, box 1 will be left behind. So if there is some friction, it will be pointing toward the right. And because the two surfaces don't move across each other, no relative motion, we use static friction. Okay, so that is the free body diagram for the top box. And for the bottom box, I guess I need to draw it somewhere else. So why don't I do this? Okay, so here's the top box. Get rid of that stroke. I'll move the whole box, whole system up, so we'll have enough space for the diagram. So this is box 1. Okay, so now let's draw the bottom box. Well, the bottom box feels gravity. It also feels a force from the top box. See, the top box feels support from the bottom. According to Newton's third law, well, the bottom pushes the top up, the top also pushes the bottom down. So there's a second force. I'll draw this as offsetted so that we can still see it. There's this force. And 1, 2. I'm using the same symbol. That's okay. It's we're going to do that. And then there's an overall support from the surface below. So there's another N. Let's call it surface. And then what else? Well, this is complicated because see the bottom pulls the top to the right with friction. That means the top pulls the bottom toward the left with the same exact friction. And on top of that, there's also kinetic friction between the bottom and the surface below. So let's draw a second friction here. This is kinetic friction between the bottom box and the supporting surface. And then against a forward applied force of F1. And as you can see, things get quite complicated because of the situation calls for it. If there's an acceleration, then the top box needs a force to pull it toward the right, and that force is supplied by the friction between the two surfaces. So let's try to do a little bit of that to indicate there's friction between the surfaces. And the two frictions here and here may not have the same exact frictional coefficient either. And this is the top, which is easy, right? That's why I start with the top. And the bottom one is less easy because all the forces that the bottom applies to the top, like these two forces, now we have these two forces in the exact opposite direction, right? The bottom supports the top, pushing it up, and it pulls the top toward the right, so it would move to again together with the bottom. And in return, the top pushes the bottom down, and it pulls the bottom towards the left. And then the rest of the forces are because of the applied force. There's gravity, the surface from the surface below, and let's call this surface S. And then there's also an overall friction on the surface. Difficult, right? There's a lot of forces. Okay, so let's move on to the next one. So the next one here is another connected system. This system has two boxes again, and we're going to ignore friction. And since we have enough space, we'll just draw over the diagram. So let's still call this 2, the bigger box being called 2, and the smaller box is a 1. So gravity pulls down on the 2. The tabletop supplies normal force. The string's pulling forward, right? But let's move that force through the center. So here's tension pulling. And over here to the bottom, the small box, gravity G1, and it's also being pulled out by the same magnitude of tension. These two. Okay, so tension must be less than gravity to allow this hanging box to descend. And then tension applies to the top, the box on the tabletop to pull it toward the right. So this is easier than the other one on the left side. But if I add friction here, there's going to be some friction. But these two systems, these two objects are connected only by a string, so they only share this one pair of forces. They're not exactly action and reaction pair forces. The action reaction pair forces are the string pulling the box on the tabletop, and the box on the tabletop pulls the string back because we don't analyze the string's motion, and that pulling on the string is no longer here. We're only looking at what the boxes feel. So with the string, there's only one additional force. These two are the same exact magnitude. Direction could change by the pulley. But if they are directly in contact like this, there could be two separate forces. The surface can supply normal force, can also supply friction. Thanks.